Started recording. Let's begin. Right. So, if you remember, before the minor exams, we basically had two classes where we were discussing representation learning, and then we moved into one of the areas where representation learning is very useful is basically the area of transfer learning. And we had looked at different flavors of transfer learning. We had looked at, say, a few short learning. Then we had looked a bit into a zero-shot learning method as well. We'll start from that point again, so that if there is something, and also I think I had to include some more components into that few shot zero-shot learning method. So we'll discuss that again to avoid any confusion as such. Okay. So, if you remember, we had described the zero shot learning setting, or before that, the few shot learning setting to be a case where you have some classes for which you have very few samples, maybe 1 or 5, something like that. That's the case of a few shot learning. And the extreme version of that particular few shot learning case was a zero shot learning case, for which you had a few samples, for which you had no training examples at all. You had some seen classes and therefore a set of unseen classes which were not seen during training, but ideally you have to perform well for the unseen classes as well, without having to look at any of its training data, which from the look of it appears to be impossible task. But we make this impossible task possible by utilizing the seen classes that we have, as well as by basically utilizing some semantic information regarding all the classes that we have. So we use some sort of semantic vectors, either it's square to big or whatever the semantic representations are there. And the name of these classes then help us to maybe guide your representation learning process. Okay, that's the general idea that gets followed in zero-shot learning. And we had specifically looked into the CADA VAE framework for zero-shot learning. And as the name suggests, it uses some sort of an autoencoder known as a variational autoencoder, which we had said that we'll discuss this in more details, the VAs, when we go to the generative models. But for now, we'll consider them as some special type of autoencoder. Autoencoder is something we have looked at in a good amount of detail in I think our first class, which is basically a network that has an encoder and decoder, and its objective is to learn a compressed embedding of that particular input, okay, which we can then use to maybe perform some other downstream tasks. The entire idea is to come up with a compressed representation, which is which does not lose as much information as which contains as much information as maybe the original image, but is of smaller size. So that way, computationally as well as say in terms of storage and all, you are at an advantage when using some lower dimensional representation of the same image. So for this particular problem, as I had mentioned again, I'll do this again over here so that there's no disturbance as such. In terms of understanding, you have some seen classes and some unseen classes. And for the seen classes, you have access to your training data as well as you see the labels. And you had your semantic vectors for the seen classes. For unseen classes, you only have your semantic vectors. So that's the difference have between the seen and unseen classes. And in this particular setup, you will be using basically two autoencoders. One will be for images, this is the encoder and the decoder, and one will be for the semantic vectors. Okay. And by the way, for our, this particular method, what it does is that these particular encoders and decoders are very few set of, say, fully connected lists. I think it's either 2 or 3 in both these cases. And what the semantic vector takes as an input are embeddings from any, say, word to vec or some other representation, semantic representation techniques, maybe BERT or CLIP or whatever you have, and then passes that vector into this particular encoder. And for the image encoder, you use a pre-trained network, pre-trained, say, large network, and you use that pre-trained network as a feature extractor for an image, and you send the image vector that pre-trained that this feature that the particular pre-trained network extracts to this particular encoder. And the job of your image decoder is to basically decode this particular vector back. Okay. And the job of your semantic decoder is to basically reconstruct this particular this particular semantic vector that we have basically taken as an input. So that's the general purpose of any sort of an autoencoder. Leave aside the concept of, say, a variational autoencoder. The objective, therefore, is to learn one single common space where there is no difference between embedding produced by an image encoder and an embedding produced by a semantic encoder for the same class. So you have a pair that is, say, x comma y. X is the image and y is the class. So the embedding of x and the embedding of y should be as close as each other. I mean, the best case scenario is basically if you can get the same embedding for both these two. Okay. And if you can do that, the what Cadavi does at the end is, once you have learned this particular setup, since for the seen classes you have both x and y, but for unseen classes you only have y, so you end up taking the y's of the seen and unseen classes, you pass it on through your encoder, and you get some representation over here. You create multiple copies of each of these classes, features of each of these classes, and basically learn a classifier for the given classes using the embeddings generated by the semantic input. And since you have the semantic vectors for all the classes, it will not matter whether you have the images for the unseen classes or not. You will still be able to train a very good, I mean, comparatively good classifier even without access to any training samples. Okay. So we had discussed these things. And one thing that we discussed in detail was the loss functions that we used in order to achieve this particular setup. So remember, we had discussed about the cross alignment loss and the distribution alignment loss. Okay. One thing which I had skipped in the previous lecture was the standard VAE loss, because these are, at the end of the day, these are types of autoencoders. Their losses were not discussed as such. Okay. So, and in fact, the losses which I described for DA was actually the VAE loss, which I basically crossed in the previous class. So SCADA VA will achieve whatever objective that we just mentioned using these three losses, not just two. You have your cross alignment loss, you have a distribution alignment loss, as well as your generic, your VA loss. Because VA loss, you're training a VA, the VA loss has to be. What they do is, basically the VA's job is simple. VA is an autoencoder. Its job is to basically reconstruct whatever input it's giving. So if the input is an image, it will try to reconstruct the image back. If the input is semantic vector, it will try to reconstruct the semantic vector back. That's the job of the semantic vector. I think in the previous class I may have mentioned this to be the distribution alignment loss, which was not the case. The next is the distribution alignment loss, whose job is not much different, but it only works with the encoder basically. So what it does is that your encoder for image and your encoder for semantic vector produces some embedding, intermediate embedding. LDA's job is to bring these two as close as possible. It tries to bring these two embeddings, which basically refer to the same pair, that is x comma y. X is the image, y is the class. But because you're using separate encoders, you might you might get a different embedding for each of these cases. LDA's job is to basically bring these two embeddings close to each other. Okay. And why do you call it distribution alignment? Because if you remember, for any VAE, as opposed to, I mean, we had just mentioned this particular setup, even though we did not go into too much detail about a VAE. Your encoder for a VAE not only produces a single, it doesn't produce a single vector, but rather produces two vectors. One refers to the mu vector, or the mean, and other is the variance. Okay. You have the mean and variance. So you have two vectors which represents the distribution around a given input. So if you have given x as an input, your encoder will basically give you a mean and a variance. And the good thing about VAEs is that, as I had also mentioned in the previous class, your encoder or a VAE, using this particular mean and variance and a Gaussian distribution, can generate a large number of samples from these set of mean and variance. This mu and variance will basically be utilized to represent a Gaussian distribution. And once you have a Gaussian distribution or any distribution, you can sample number of embeddings. So a single X can give you a lot of good features or multiple features that belong to the same class Y. So that we are also, in a way, dealing with the situation that at the end of the day, you will be doing something similar with the semantic vectors. You have just one semantic vector per class. So if I give you just one sample per class, that is basically if I use an auto encoder rather than a variation auto encoder, and I just have one semantic vector per class, I will have for 10 classes, I'll just have 10 examples, for which it's very difficult to come up with a good classifier. It will be too less a data to be of any use. So this is where the advantage of using a VAE comes into play. The VAE can generate multiple representations, not necessarily the same value gets repeated. You will get some variance in the representations as well from the same input. So that's the basically the job of the VAE. VAE learns to deconstruct the original image or the original semantic representation. Okay, but during the next phase, when you basically have to train a classifier, VAE is also utilized to basically come up with number of embeddings from the same X or the same say S, and using that multiple embeddings, you can actually then classify. So we'll get to that. We'll get to that once we finish these three losses. So you have your VAE loss, you have your domain alignment loss. The domain alignment loss because you want to bring these embeddings as close to each other, and the embeddings in this case are in the form of a mu and a sigma vector. You will try to reduce distance between the mu or the mean and reduce the distance between the variance. And there is some expression for that you can refer to the paper for. But the general idea is you reduce the distance between these two distribution, or specifically you reduce the distance between the mean and the variance. So if you can make them the same, that's the ideal scenario. You get an embedding, common embedding for both your image as well as your semantic. And finally, you have your cross alignment loss, whose job is to basically map the wrong decoder to another encoder. So if you have an encoder and decoder for images, you map the encoder for your image to the decoder for semantic vectors. So given any input, say x comma y, you get an embedding through your image encoder, but you send that encoded embeddings to your semantic decoder. And the semantic decoder, whatever gets extracted, that should actually match the semantic vector that has been initially pasted into, say, the other encoder. So sort of a cross alignment setup. You have your encoder decoder for your image and encoder decoder for your semantic vectors, but then you cross alignment does this cross mapping. And both your cross alignment as well as distribution alignment serves a single purpose, that is you're trying to bring the image embeddings and the semantic embeddings into the common subspace so that there is no difference between them as such. And once you can achieve that, why are we trying to do this? Once we can achieve that, since we only have semantic vectors for your unseen classes, we can now use semantic vectors to also generate embeddings for your unseen classes as well. And with that, we can now train a good classifier that can classify both your seen classes as well as your unseen classes. Okay, and that's the general idea of how this is working. So, any confusion up to this point? If you have that, please let me know. Was I audible or
Yes,
hello?
sir.
Yes,
Yes.
yes.
Did I just get disconnected or hello?
Yes, sir, we can hear you.
Okay, so did I finish this slide or was I
Yeah, yeah.
still?
Yeah. Sure.
Okay, 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 fine. Anyways, any doubts up to this point?
Not at all. Good.
Okay, okay.
Sir,
So
can you
let's, yeah.
just explain the DA again? DA loss.
Domain alignment. Yeah, so distribution alignment, right? So distribution alignment, as I can show you again over here, basically this autoencoder, this variation autoencoder will produce two things. One will be the mean vector, one will be the variance. Similarly, mean vector and variance vector. Okay. Now you're giving as input the image and the semantic vector. Okay. Now, ideally, since these two are different VAEs, these mu and sigma squares will be different because this input is different. This is a semantic vector and this is an image vector, image feature. So initially this will be different. So what domain alignment does is tries to make these two means the same and these two variants the same. If you can do that, it will not matter which encoder you're using. You will get basically the same or at least similar embeddings, whether you use the image VE or the semantic VE. That's the job of your domain alignment loss. So you simply reduce the difference between these two mean and reduce the difference between these two variants. That's the general job. So any confusion in this part?
So, sir, can we say that this is trying to bring the distribution as close to each other as possible?
Yes. That's the whole point. Because see, for your VAs, even though we have not discussed VAs in that detail yet, the idea is that the once you give anything as an input to your VAE, the encoder produces a sort of you can consider this as a Gaussian distribution only with a mean and a particular variance. So you will have something a similar Gaussian distribution for this the semantic vector as well. If you can make these two means same and these two variance same, then you end up with the same distribution. So you're aligning these two distribution. That's why it's called distribution alignment. Okay.
Sir, once again, CA loss as well.
The cross alignment loss.
Yes.
So what cross alignment loss does is you have your image encoder and you have your semantic encoder, and you have a pair which is x comma y, where x is the image and y is your class. So for the image, you have some image feature from some pre-trained model. So you have an image feature, and for semantics or the class, you have a semantic vector from say other word to vec or some other word embedding options that you have. So when you're training a simple VAE, you will ideally not be performing any cross alignment. So your this particular image encoder will produce some embedding over here, and that embedding, when decoded, will produce it will try to reconstruct the initial x. Okay, and similarly your VAE for semantics will try to reconstruct the original semantic vector. Okay, now that's the general setup. What cross alignment does is it will take the embedding of x generated by image encoder and pass it on to the decoder of semantics and generate a y that should match the original y of this particular pair. So you are taking an image as an input but trying to reconstruct the semantic vector from the image vector. Similarly, you take a semantic vector as an input to your autoencoder, but try to generate the image from your semantic vector. Okay, that's the idea of cross alignment. You're crossing both the VAs. You're mixing, matching the encoders and decoders for both the VAs. And the overall objective is that you want to, at one stage, you want to be able to utilize any of the encoders and still be able to generate data with the same within the same distribution or same say space. That's the general idea for both your say utilizing your cross alignment as well as your distribution alignment.
So, sir, I have a question, right? When we decode the semantic, right? So, how we get the uh, encoding of the that vectors embedding? Like, we have any information kind in the semantic?
No. So you want to know when we have. Can you repeat the so? Let me give you the setting first. You have both x as well as y for your say for your, at least for your scene classes. X is your image vector that is given by some pre-trained model, and y is a semantic vector of that class that is given by say word to vec. Yes. Now you ask your question.
So when we generating the embedding from the semantic, right?
From the semantic, yes.
Yes. So how we can generate, like, is there any we have any weights around there or any kind of like vectors in the semantic, because
This
semantic is the
particular
only classes, right?
class names are there. So I was assuming that you are aware of word embedding
Yes.
options like say word to vec. Are you aware of word to vec or say bird?
Yes. Yes. Yes.
So they take some words and produces a representation for those, right? So class is also you can represent it as a single word or say multiple words. You have a class say cat, dog. So if you pass cat or dog to any say word to vec or some other language embedding models, you will get a representation vector for that particular word, isn't it?
Yeah. Yeah, that's fine. What we get
Huh.
from the what to wake, like if we
Yes,
apply the cat, then we get the uh,
some embedding
vector
from that.
form. Yes, vector
Huh.
formation of the that cat word.
Yes,
But
yes.
after that, how we get the uh, like
This particular embedding,
not x? How we get the x from there?
X we don't. Acha, how you get to X from here? You're saying?
Yes, no, not
Yeah,
me.
we don't get X from here. You this see this E2 and D2 are for semantics.
Uh,
So the encoded information is a semantic vector. The decoded information is also a semantic vector only.
hmm,
Okay. What we do is that we take this encoded version of, say, the semantic vector and pass it to the image decoder. Now, image decoder is used to taking a vector as an input and producing an image as an output.
okay.
Okay.
Hmm.
So
So, but
if I give you any vector over here, it will produce some image.
okay,
Now, what cross alignment does is it will force it to produce reconstruct X, this loss,
oh,
even though I have not given the embedding of X to D1.
so it's trying to cover the loss.
Cover the loss?
Sorry.
No, repeat your question.
So it's trying to like uh, si- uh, getting this similarity between that x and what we decoded x, right?
Yeah, yeah. Okay.
Sir, one question. Actually, we are using two encoders and two decoders, right, sir?
Yes.
So,
Yes.
for our problem, for our assumed problem,
Mhm.
only three components are enough, right, sir? Two encoders, one decoder. That below bit decoder is enough for us, right?
No, no. But this particular encoder should learn to produce some good representation so that the semantic information can be extracted from here. So we
Semantic.
need
Okay, that
huh?
decoder is not useful for us, right, sir?
You
Because
add
our problem is we are having the less data for images.
yes,
For
yes.
that purpose, we are using the embeddings, text embeddings. So we are combining
Huh.
both, and we are able to reproduce the unseen image at the uh, downside of the downside decoder, right? So that's enough, right?
Huh. Huh. Yeah. No, but the thing is that this image that you generate will not be a perfect replica of the X.
Okay,
Well,
okay.
generally, it's very difficult to get a general exact replica of X, and also because this semantic vector will be common for a lot of X, X1,
Yes,
X2. Suppose X1, X2 both belong to the same semantic vector.
yes, yes, yes.
So while encoding, you have a single Y for multiple X. So this reproduced X that you generate will not necessarily be representing exact versions of all X's, but what you can achieve is that because this particular variation autoencoder is produces a mean and a variance, you can sample multiple at least embeddings at this stage. Okay, which will serve as which will basically be utilizing for our next work. I mean, for our subsequent task of training a final classifier. So once this particular training is done, what we'll do is that we'll discard this entire setup and we'll only use the semantic encoder. We have the semantic encoder, semantic representation for both seen and unseen classes. We pass it to this. We get, say, for every class, we'll get a mean and a variance. And with that, we'll produce a lot of vectors, not images. And what we do is that based on these vectors, so I generate say 100 vectors for each class. I'll now train a classifier. Okay, and once we have a classifier, given any test image, what I'll do is I'll not utilize this part for at least learning the classifier, but I can at least utilize this part for getting the representation in the same space. So I'll pass that representation now into my classifier and I'll get an output for this.
So what will be the impact of second input on this classifier?
Impact of second input. What is second input?
Two input, right? We have bottom one, another, right? Gray part.
Second input means the semantics.
Yeah, semantics, yes.
Semantics also will work, no? Because you have trained the classifier based on the encoded versions of the semantics only for all classes. So whether you give it a semantic vector as an input, okay, in which case you'll have to encode the semantic vector and pass this particular setup to your classifier, or whether if you have an image, test image, you extract the feature for the text image and pass it to the classifier. Both these cases, your classifier is supposed to work well because you have ensured that both this encoder basically produces embeddings that are close to each other, given that they are from the same class.
So any one input will enough, right?
Any one
Either
input is
either
enough. Yeah.
semantic or image.
While testing, no? While testing, you obviously will get only images only.
Mhm.
Because for testing, you have access to both seen and unseen class images. But for training, you don't have access to training images of the unseen classes.
So, sir, if in practice X and Y, they they have entirely different distribution. I mean, even though Gaussian, but their mean and variance lie,
Yeah.
apart, quite apart, and so it
Huh.
sort of forces it to be the same, right?
Yes, yes, yes. That's the job of, say, your distribution alignment.
Right, but
And
then,
also, it's also, I mean, cross alignment also plays a similar part.
will that cause any loss? I mean, loss in the sense that, I mean, one might be completely overpowered by the other sort of.
No, that's why when you apply cross alignment, you do it for both direction. You don't only do it for the, say, your image encoder and the semantic decoder. We also do it for the semantic encoder and the image decoder. So you are giving equal importance to all portions of this process.
And can this be
Obviously, see,
like,
obviously it's a zero shot setting. You cannot expect to get the same performance as a simple setting where you have enough data for all classes. That will be sort of your upper limit. So you're making do with something less. So there will be some trade-offs that you're making, like you're forcing the semantic vectors to come to the same distribution as your image encoder. You definitely will lose some or the other information. That is granted. But that's the trade-off that you're willing to make so that you can at least build a classifier for some unseen classes.
can this be extended to, say, we have image and text? Can we
Uh-huh.
add a
So that's the
third one?
beauty of this thing. This particular Kata VE setup, you can extend it to multiple modalities. You can have one for, say, audio. You can have one for, say, IR images. So that's the beauty of the Kata VE. You can extend it anyways that you want. And accordingly, your domain alignment and cross alignment, the number of individual subcomponents of that will increase. So that's why I wanted to cover this because it takes some time to understand, but it's actually a very useful setup, and you can generalize it to multiple domains. I mean, you are already using semantics and image. You can extend it to further domains as well. Okay, right. So the next thing that we also, this is the testing setup that I just described, which is before testing, the multiple semantic embeddings of seen and unseen classes are obtained using the semantic VE, and the classifier is trained on them, and that classifier then is used for testing. That's what I basically described over here. Okay, and this is the, I mean, the loss. You have the VA loss, you have the cross alignment loss, and the domain alignment loss. Initially, you will perform the VA loss for a few epochs. I think they do it for 6 epochs, and once that is done, so the at least the VAs are good enough in at least reconstructing their own type of output, our own type of input. Then you introduce your cross element and domain element processes. Okay. So with this, we are done with, say, zero shot learning. You can basically, it's such a basic idea. You can now extend it to a lot of setups. I mean, you will see that this particular idea can be utilized in other setups as well, where you have, say, limited data, or say you have multiple types of modalities to deal with, and you will get some good results even in those cases. Right. The next setup is known as incremental learning. And all of these things are sort of some way related to transfer learning only, because we are transferring the useful representation of one particular set of classes into the representation into to help say another particular set of classes for which you may not have good enough information, maybe limited data, or maybe limited labeled data. You might have a lot of unlabeled. So the next setting that comes into play is the incremental learning setting, which, as the name suggests, you incrementally add new training data, and your classifier that you train should be good enough to perform well on all kinds of classes, whether the classes have been introduced much earlier, or whether the classes have been introduced much later. And the idea is that, I mean, we'll look into the detailed setup, but whatever we try to do is that we'll, at every incremental learning stage, we'll introduce some new classes altogether. Okay. So by the end of the time, I mean, not the time, I mean, by the end of, say, a particular, if you take any particular stopping point, whatever classes you have seen up to that point, your classifier should work well on all the classes. Okay. Now, this is sort of a tricky problem. And say, initially, I give you 10 classes and I give you 100 examples per class. And then again, at the next stage, I give you another 10 examples with another 100 examples per class. So this data keeps on growing. Ideally, if you simply train, you take all the data that you have and train a new network on top of it, you can resolve this problem at one go. There is no need for any special incremental learning algorithms. You simply collect all the data that you have at that particular stage and train a new model on. But then at some point, this becomes a costly endeavor. You don't want to always retrain a model from scratch, or I keep on storing that large amounts of data for all classes. So that is a problem. Now, what incremental learning setting does is that it will stop you from storing the entire data of the previous classes. So if airplane and automobile have, say, 1,000 examples each, incremental learning will either not allow you to carry even one example forward, or maybe allow you to carry just maybe say 100 examples. So 1/10 of forward. Okay. And that is where the problem comes in. What you now have at this particular setup is either you have, say, your full 1,000 images of birds, but you may have no images left of automobile and airplane, or maybe you have very few images, only say 100 images. If you now train a classifier from scratch, this classifier will be fully biased towards the new classes. Okay, it will not perform that well for your older classes. So the other option is, let me not train a new, training a new, new classifier, new model itself is a costly process. So let's not do that, time consuming and costly process. Let's not do that. What I'll do is that I'll only fine tune on the, say, new set of classes that I have. If I do that, if I fine tune on the new set of classes or whatever data I have available, again, because the new class has a lot many more data as compared to the other classes, the model will start performing very well for birds, but it will start performing poorly for airplane and automobile. Now, suppose this is complete and you move to another task. Now, all of these are older classes, airplane, automobile, bird, and all of these have less data available for you. And for dog, you have large number of data. So what will happen over time is that you will start forgetting the previous classes slowly. And your current class performance will be very high, okay, which is not ideal. Ideally, when we have a classifier for, say, 5 classes, I want it to perform well for all the classes that I have. It should not matter whether I have introduced some few classes at a later stage or some at an earlier stage. For all old and new classes, your network should work well. And that's the idea behind incremental learning. General deep learning cannot deal with this particular problem. General deep learning will require all of your classes to have sufficient data in order to perform well on all the data points. And if you don't do that, what will happen is you will suffer from this sort of a forgetting of previous classes, which is what we try to avoid in, say, incremental learning. Okay. Right. So incremental learning is another form of transfer learning, where the model has to train on a sequence of tasks. When I say tasks, I'll say for each task I introduce one new class, or say 2 new classes, something like that. So task is a set of classes and their associated training examples that you have. So, and it has to perform well on all the tasks. That's the overall goal. Because we generally refer to us as humans, we see new things, and even though we might forget some things that are that we might have observed very long back, we generally retain the ability to quickly relearn those concepts. Like, say, if I tell you how to plot say a logarithm on a particular graph, and if you have not connected with plotting graphs for say 10 years or so, you might forget how to plot a graph. But then if I show you one example about that, you will quickly remember what you have done, maybe say in your school life, and will be able to quickly adapt to and perform well on plotting graphs as well. Okay, so as humans, if we can do that, why can't we transfer that same ability to deep learning models as well? Okay, and in any case, incremental learning, if you want to build an AI that is actually like humans, it will have to accumulate new information over time, and it should be able to utilize all the information it has seen previously as well as the new information. So it's a very core concept of getting a very uh, advanced, say, AI model. Okay. So in this particular setting, the data will be provided to the model that you have in the form of tasks, and each task will have a set of non-overlapping classes and their associated training images. Okay. So between tasks, for now, we are assuming there will be no overlap as such. So if the first task was airplane and mobile, the new task is bird, no overlap, and the third task is dog, okay, only dog. So generally, you will have more than one setups,
Yes, sir.
classes in a task.
One
Yes.
general question, like
Yes.
I'm not able to understand like why we are introduced as an incremental learning. Like what incremental is happening here?
You're
But
incrementally learning to classify newer classes.
means adding new
That
class
is,
is the incremental.
yeah, in this particular setup, we are considering that to be an incremental learning.
Okay.
So what we have a get the new data.
Hmm.
So in the same feature, so it's kind of can we take in the incremental learning?
No, no. Can you repeat the question again?
So if
Acha,
we have
new
a
data, but for the same set of classes.
yes.
So that is also another form of incremental learning where the classes remains fixed, but your data sets, I mean, you get new set of data every time.
Yes.
So if the newer data that is arriving has roughly the same variance and distribution of the original data, then there will not be much problem. Okay, maybe say if you're say classifying for cats and dogs, you get all varieties of cats and dogs in the Indian subcontinent, and then suddenly you get a new set of cats and dogs that are from Egypt, and suddenly you see that your initial model, which was working fine for say cats and dogs, is not working fine anymore on this new set of data. Okay, that is also considered incremental learning. So there are multiple settings. We are considering a setting where you are increasing the number of classes at every stage, and you're getting new tasks, new classes at every stage. Both of them are qualifying as incremental learning.
Okay, so in the both of the case we actually forgetting the old feature
Yes,
old
that will happen.
old data.
So that will be more pronounced in this particular setup where you're actually getting new classes. So you'll start forgetting the older classes. In the case where you have data that is increasing but the class is remaining the same, if there is no distribution shifts in the new classes, in the new examples that you're getting, so you're getting again the same sort of distributed data, same input distribution, then the performance will not change. But if you have different distributions, like I gave you an example, see if you have Indian cats and suddenly you start including Egyptian cats, what will happen is that your classifier will now train on say your Egyptian cats, which has say more data, but will now perform poorly for your Indian cats. Okay. Will not be may not be as confident, or maybe even start misclassifying them. Okay. So this problem exists whether you're increasing classes or whether you're increasing the data over time. And this problem would not have been there if you had infinite storage and you could have stored the entire data. Then this problem would not have been there. Also, if you had ignored the cost of retraining a model, if that is not a matter for you and you have infinite storage, then that's fine. There is no requirement to come up with a special algorithm for incremental learning. But generally you don't tend to have that much space, or you don't want to spend that much time maybe retraining a data, especially if you have not trained your model, you have borrowed the model from some other agencies, if you want to again retain it, you might have to again pay some of these agencies again. So that's where your incremental learning setup comes into play. Okay,
Okay.
great. So in this particular setup, the model will have access to only a single task at a time, okay? But it is expected to perform well on the previously seen tasks as well. So after every training session of the model on a particular task, it will receive a new task. And generally what will happen is that you'll not be able to retain the full data of the previous task. Okay. In some settings, it's even stricter. You'll not be allowed to return even any single image from your previous task, and you're only getting access to newer images from newer classes. So that will be one extreme case of incremental learning. So there are different flavors of it. So a class incremental learning will increase, say, one class at a time. Okay. And also in some cases, class incremental learning and task incremental learning, both will introduce new sets of classes at a given time, but your task incremental learning will only expect you to perform well on a particular task, and it will also mention you which task to perform well on. Suppose in first task you get cat and dog. In the second task, you get car and say truck. Okay, and the third task you get say ball and say a plane. Okay. So these are the three tasks that you have. So your class incremental learning will expect you to perform well on all of these 6 classes. And generally, the task incremental learning is a setup where you will actually be made aware of which task for which your current test image belongs to. So while testing, if I tell you that your test image belongs to task 1, then I'll already know that I have to either classify it as a cat or a dog. If I tell you if it belongs to task 2, my problem reduces to only checking between car and truck. So task incremental is generally an easier setup compared to class incremental learning, where in class incremental learning you have to perform well on all the tasks, and you have no identity available for your test images belonging to which particular task. But for task incremental learning, we might provide you which task this test data is coming from. So that way it's an easier setup. But in general, you will suffer this forgetting problem in all of these cases, because as you encounter new classes and train on them, you'll start forgetting the previous set of classes. So your objective is to learn a good classifier for both, say, old and new classes or tasks. Right. So, as I mentioned, once you get a new task which contains a new set of classes, and the available training data that you have is dominated by the new class only, or the new task only, and you have very low or even say no training data of your previous classes, you will start forgetting the previously seen classes. Okay. And then your model is basically not as useful as before, so you want to avoid such situation. This particular phenomena is also known as catastrophic forgetting. It's a very famous term in incremental learning. Okay, right. So, what are the approaches that are generally used to solve incremental learning? And we'll see 2 basic approaches which are used in all incremental learning setup in some way or the other. Okay. One part that is one method that is, or one general approach towards incremental learning is basically what you can do is that you can reserve a portion of your model that is common to all classes, even if you see new classes, and one portion that is restricted to a specific task or a specific set of classes. Okay. So if you can reserve a portion of it, then you have an advantage that you are basically dividing the available parameter space into different classes, but then your model size is fixed by default. So after a given point of time, you will not have enough parameters to give to a new set of classes. So there are some approaches which solve incremental learning through this process of reserving a portion of your parameter space, but then it is not scalable to very large problems. Okay. The other option is, which is a very naive option, is to basically grow your model to accommodate new classes. So you keep adding new branches whenever you get a new set of classes. Maybe the final 3-4 layers you can create a new version for every new set of classes that you get. But obviously, while training, you have to train them jointly so that you get a common prediction for your entire network. But then this is also, it's even less scalable because you're expecting to get a lot of classes, and as time goes on, your model will become larger and larger, which means the training time increases, the inference time increases, the computation and storage requirement, all of these things are increasing, which is also not a very ideal thing. Okay. The other option is, which we'll see in some detail. We don't have enough time today. We'll see maybe more details in tomorrow's class. But the other option is that you prevent the model from changing its output for the classes that are previously seen. Okay, we'll see how to do that. So suppose your model is to produce for any given image for two classes, say cat and dog, it is to give some distribution was maintained between, once you have learned a classifier for cat and dog, it produces say cats and dog with some probability. So we'll try to ensure that even when I see another new class, at least for the first two outputs, that refers to your cat class and your dog class, your output should basically remain as same as possible as the previous model. We'll see how to do that. It might not seem very logical at this point, but when we see an example, that will become much clearer at this stage. And the good thing about this particular first setup is you don't need to store any images from your previous set of classes. So that way it's a very scalable approach. But since you're not storing images from your previous set of classes, there's a limit to how much you can improve your performance using this particular approach. And there will be forgetting still, but you can at least, it's a cheap way of controlling forgetting, okay, without having to store previous class data. The other option is you retain a very small set of samples from the previous classes, okay, and use them along with your the new class training data that you have in order to perform well on the new classes, as well as you're able to preserve the performance on your previous classes. And this preservation of performance will some way utilize this idea as well. You'll prevent the output of the model from changing too much for at least the outputs of your previous classes. And these two techniques are generally the most widely used approaches to deal with incremental learning problems in the setting that I just described. Okay. And even the recent methods will use some of the other approaches of some of the other versions of these two approaches. Right. So a very important point say very important method of doing this particular approach is known as knowledge distillation, which we'll cover before going to first approach of say your incremental learning. And this particular approach is known as knowledge distillation. Okay. It's generally also known as say training a student network from a teacher network. You're transferring knowledge from a teacher network to a student network. And this involves, I mean, at the basic level, it involves only two models. You train one model first. Okay, that is known as a teacher model. Once you're done training, you train another model whose work is to still maybe make the same predictions, but it will also utilize the teacher model as a guiding light to help it perform better. So we'll see how to do that. That's the general idea of knowledge distillation, which is extensively used by incremental learning techniques. So we'll first look at basic knowledge distillation, and then we'll use it. We will show how to utilize it in, say, your incremental learning. So knowledge distillation generally involves transferring knowledge from a pre-trained teacher model to a student model. And generally, the student model is a smaller model. So suppose if you have trained a very large model, say less than 50, and you want to deploy it on your, say, mobile phones. So nowadays, mobile phones have a very large memory. You get 16 GB RAMs and all. But suppose if you don't want to make the application too heavy, you want to run a lighter model on your mobile network. So you have two options. Either you train a smaller model on a particular, on the same data set, in which case your performance might not match with the larger model. I mean, generally it will not match with the larger model if you're running it with the same batch size and same other losses and all. Or the other option is that you distill a smaller model from a pre-trained large teacher model, and that distilled model might be somewhat similar to, in terms of performance, very close to your teacher model. And that way you are somewhere midway between using a very large model or very small model. You're somewhere midway where the performance is between these two. Okay. So you want to trade off the say size requirement as well as the performance requirement as well. So you are using a smaller model, but it has a performance that is maybe closer to your larger model. That's the general idea of utilizing knowledge distillation, and we'll see how to roughly do that. Okay. Self-distillation is a case where the teacher and student models are basically the same architecture. And it has been observed that while distillation helps improve the performance of a smaller, simpler model, if you use the same architecture for a student model, it turns out that you can actually improve the generalization power or performance of the same model, same architecture again, if you're using, say, a teacher to guide the process of training for, say, classification or other objectives. So what we do is that in order to transfer this knowledge from a teacher model to a student model, we'll obviously have to train, say, if you're doing it for classification, you anyways have to train the student model for classification also. But what you will also additionally do is you will shift the output that the student network produces closer to the output of the teacher from the same set of images. So if you're giving an image X to your teacher model and you're getting some, say, set of probabilities as an output, you will give the same X to your student model and you will try to basically make this output probabilities that is produced same as the one that a teacher has produced. Okay. So in a way, you're forcing it to give, say, a better result of your teacher, which your teacher has learned through a lot of pre-training and all. So you're trying to force that information or force your student to produce exactly that probability distribution that your teacher is producing. So that's the general idea of knowledge distillation. There are ways of basically doing this knowledge distillation, which will involve reducing the gap between the output that they are producing. So as suggested earlier, you will require a classification loss anyways for your student, because at the end of the day, student has to make some predictions. But it will also have a knowledge distillation loss, which we'll see how to do. Okay. Knowledge distillation can be done in many ways. You can either use a simple MSE loss. Simply, you have two output vectors. You simply take the mean squared error loss and try to make them the same. Or the other approach is to do a KL divergence loss. So what KL divergence does is that it takes two distributions and returns 0 if the two probability distributions are basically the same. Okay. So in this particular setup, if you utilize a KL divergence loss, even though the individual values may be different, but when you calculate the probabilities, it will try to ensure that the probabilities of all the classes produced by the student model matches the probabilities of your teacher model. Okay. And generally, we use the KL divergence loss for knowledge distillation. Okay. So I think we don't have much time left for today's class. We'll continue on this setup tomorrow. So any doubts up to this point?
So what is soft labels and hard labels mentioned?
Yeah, we'll discuss that in the next class. The general idea is that your hard labels are in the form of one hot vector. So if you have, say, 3 classes and your image belongs to class, say, 0, 1, 2, your image belongs to, say, class 1. Your ground truth generally looks in this way. Okay, your ground truth will have zeros for the other classes, which are incorrect classes, and a hard 1 for the correct class. Soft labels are generally not in this format. Soft labels will be somewhat like, say, you have 0.1, 0.1, and 0.8. Okay. So what this does is that not only am I forcing you to learn the correct class, but I'm also telling you how much the contribution of the other or the possibility of the other class will be. Okay. So that's why these are soft targets rather than, say, hard targets that you have. Okay.
Okay.
Any other doubt?
So for incremental learning, why can't we use like when we get a new class, why can't we just train a new model, and at the end of that, right, we will just take some kind of a voting system and then predict the output.
So the new model that will train it only on the new class.
Yes. Yes, sir.
So then how do you know, say, given any image,
Hmm.
how do you know which class it belongs to? Your new model, you suppose your old model can predict, say, cat or a dog,
Hmm.
and your new model can predict a car.
Hmm.
And you give the same test image.
Right.
You have not trained your classifier to give higher probability to car. compared to cat and dog when you have a car image, and you have not trained this particular model to give a higher probability to car when you have a car image sent to the old model. So you will not be able to find how to judge which class this belongs to if you are using a separate model.
But sir, the if I have like two different model and I give a car image, so the output of the car model will be higher, right, as compared to cat and dog. So
It's that's the point. There's no necessary thing that this will be the case. Maybe you can look into this as well. This is something known as, I'm forgetting the term, but it's the concept of confidently predicting the wrong input, wrong result. So models. So at the end of the day, these models are all some part ways. These are all, say, mathematical function, and when you have trained it, for cats and dogs, even if you give one image of a car, it will try to map it to either a cat or a dog. Okay. And maybe it will give you a higher probability for a dog. Say, maybe it's not that high, but say, suppose you're giving, say, zero point 0.5 and zero point 0.5,
Hmm.
and suppose, or say, 0.6 and zero point 0.4, and suppose over here for car, you're getting 0.5. Suppose, I mean, there is no guarantee that if you're for any test image for a car, your model will always give, say 0.9 or zero point 0.8. That's generally not the case. Now the point becomes, if I consider them as one and I try to take the maximum, my car might get predicted as a cat. This problem occurs because your model has not seen a car image during training. So but it knows only how to predict between cat and a dog. So it will map one of your images to whichever is similar in terms of, say, features. It will map it to one of them. Okay. And it might turn out that your overall prediction that you want to take based on maximum, say, value output, it might give it to the wrong class. So that if you can also try this out as an exercise. That's a big problem that will occur. You can try this out as an exercise. For some images, definitely, for some images, you will get maybe this is high, but there's no guarantee that this particular approach will always work.
okay.
Okay. Okay. We can discuss further in the next class. That's tomorrow.
Sir, can you post the video recordings?
Close the video.
No, can you post the video recordings in the classroom?
Oh, post the video. Yeah. Okay. So I think this takes some time to generate. I think the video comes generally in the evening sometime. I'll then upload it. I'm stopping the recording.